Today we're going to talk about scaling your time series data with Newts. So in particular, we're going to talk about what Newts is, how it works, how it integrates with OpenNMS, and hopefully by the end of this, you'll be able to determine if Newts is right for your particular use case. So a bit about me. I'm Jesse White, so I started off as a user in the OpenNMS community. In my particular case, we developed some enhancements for a company. Then I was a student for Google Summer of Code. And as of a year ago, I've been working for the OpenNMS group, and now I'm CTO. So,
meteoric rise.
What's that?
A meteoric rise.
A meteoric rise. Right. So that said, let's talk a little about Newts here. So for those of you who don't know what Newts is, it's a time series data store based on Apache Cassandra. So it's primarily designed for scalability and high throughput, and it achieves that by leveraging Cassandra where it can. It differs from most of the other time series solutions in that it performs late aggregation instead of calculating the averages at write time. So what that means is you get faster reads, and then you calculate those whenever you read instead of write. So that allows for much more throughput. And so Newts is packaged as a Java project, so you can either embed it as a Java API within your project, or alternatively, you can deploy a REST server and use it like that with any languages you like. In the case of the OpenNMS deployment, we just embed it as a Java library. So you can think of it as kind of a gateway to Cassandra. That said, Newts is not particularly tied to Cassandra. It could technically support alternate key value stores to back it as well. But for this case, we'll strictly be talking about Cassandra. So by a show of hands, is anyone familiar with Cassandra? Somewhat? OK. So I'm just going to go over quickly how it works and some Cassandra basics, but won't dive too deep in that. It's fairly complex, and there are tons of existing resources out there that can do that a lot better than I can. So at its base, Cassandra is a distributed hash table, right? So you have a series of servers that you call a Cassandra cluster or ring, and it basically acts as a key value store, right? So you go to look up this particular key, it'll give you the value stored in that block. And it achieves this using the distributed hash table. So keys are typically evenly distributed against all of the nodes in the ring. And whenever you want to read or write data, you talk to a particular node, and that one will act as the coordinator for your request. So even if that node that you're talking to doesn't actually have the data, it'll coordinate and go and get the data from the other nodes that do in fact have it, right? So with this design it has, it's very decentralized. Your data can be replicated. It's scalable, fault tolerant, and has linear scalability there as well. So we chose that as the data store backing for our time series data. So in a nutshell, that's Cassandra. So let's talk about Newts now. So Newts has a couple of core concepts in its data model. So at the top level, there are resources, there are metrics, and there are samples. So a resource is something like an interface, or a hard drive, or this particular server. So resources are identified by a unique string, just like they are within OpenNMS today. So a resource is at the top level there. Then a resource can have one or more metrics. So those are the blue boxes lower down, right? So looking back at the interface example, you might have your if-in octets, if-out octets, various counters, et cetera. Those counters will then have values, which we call samples, and those will be stored at various times, right? So top level, we have resources, metrics, and samples. So what we're looking at here now, this is the actual schema for Cassandra. You can kind of think of it as a SQL table, if you can relate more to that. So I'll just kind of explain this so we can better understand, how the data is structured and how we query that. So one of the important things here is this primary key field, right? So there's this first part that's in parentheses, and then the whole thing is in parentheses as well. So that is a composite key. what really matters is this first bit here, right? So to look up the particular samples for a resource, right, we need to know the context, the partition, and the resource. So context is basically like an application-specific constant. So within OpenNMS, we just use a single constant. I think it's called, it's a capital G for global context. But what that allows you to do is have overlapping resources in different applications that use the same table, right? Then we have this partition bit. So partition is basically a period of time. So what this does is it groups all the samples, so all the values in a particular bucket, right? So that partition key is a configurable size. By default, we set it to 7 days. So all of the samples for a particular resource in a constant will end up in the same bucket for that period, right? So that's the information that we need to be able to access the values in this spot. So there are a couple other values in this key as well. So those are used for two purposes, one for ordering and two for uniqueness. So by having those additional keys, we make sure that we only have one sample for one metric at a particular time, right? So that's the key portion. So we touched on most of those bits. And so the samples themselves have the actual value, which is stored as a blob here. So that's basically a 9-byte value. The first byte indicates the type, whether it's a double or a long, and the remaining 8 bytes are the actual number, right? So samples can also carry attributes, which are text key value pairs. So you can tag your samples as they come in with additional metadata. And whenever you query it, it'll sort of aggregate those all up and give you the list of attributes. So at its base, all of the samples and metrics that are collected in OpenNMS will be stored in this single table here, right? And they're going to be distributed among the Cassandra ring based on this key. Right. Is that clear for everybody? Makes sense? Cool. So one of the things here is that in order to be able to get the samples out of this table, we need to know the resource ID. In a lot of the cases, we don't know the resource ID. We kind of want to be able to see what's there, what have we collected. You know, we want to be able to just list that instead of keeping track of that elsewhere. So there's an additional table. This is a table that we use for indexing. We call it the terms table, right? So again, all the fields here, we'll go over the primary key. We have the context, field, value, resource, right? So what that'll allow us to do is say, in this context, I know the field, I know the value, give me the list of resources that are associated with that. So we'll touch on that more in detail later, but just to give you an idea of what the table layout looks like here. Right, so here's an example of a sample, right? What this is in our case, this is a sample taken from our vending machine at the office. So we're keeping track of the cans of cheerwine that have been sold with the counter, right? So this is saying the resource ID is Ike, which is the name of the machine, : vending machine. That's our resource. We have additional attributes here. We're saying, you know, that particular slot holds some cheerwine right now. At that particular value, the counter for slot sold, its value was 8. Right? So we can store that within the first sample table, but we want to do some additional work so we can go ahead and find this resource later. So the way it works is the resource ID is actually split on the colon. That's our marker there. And in that terms table that we saw earlier, we're going to go ahead and add those fields and values, right? So what we're going to do is add, let's see, for every little bit here, we're going to add it in the all field. This bit, we're going to add it in the all field as well. And we're going to add this particular key value pair. So what this allows us to do is then create queries and search for particular resources, right? So to find this resource ID, there's several queries that we can do. So there we use a Lucene-like query syntax, right? So the first query, we're just looking for cheerwine. So if there's no field specified, that'll default to all, so we'll search it all. Second, we can actually specify the explicit field we want to search. So I'm looking for the resource that has, that's holding cheerwine in slot 15. And on the last search, what we're doing there is, looking for any resource that has cheerwine and either Mountain Dew or RC Cola, right? So we can do those sort of compound queries. But one of the limitations with this is that we can't do those sorts of searches server-side, right? Because we can only retrieve the values at that particular key. So what's happening behind the scenes here is we're actually got to pull all the data for the various keys into memory and then merge the results. So what's really important is that these fields be properly indexed from the start. So you want to try and avoid queries of that last style and use only queries of the first 2 bits. Right? Okay, so that's a bit of the back end on Newts and how it works internally. I think it'll be a bit clearer as we dig into how it works with OpenNMS. So now we're going to switch over to OpenNMS and how the existing data collection stack worked. So traditionally, OpenNMS only used RRD tool for its persistence, right? So we use RRD tool style graphing. Everything was already everywhere. So the code base assumed that it could just look on disk and see these RRD files and always right there. So to get something like Newts into OpenNMS, there's a lot of work to be done to sort of abstract that concept, right, and break that out. So a lot of the work in 17 to get Newts in there was mostly creating a layer of abstraction between persisting the data and getting the data back out. So that's a graph of our cans of cheerwine sold in the office. As you can see, there was a big consumption there during those first few weeks. I think that's probably when the Germans were in town. So here's how we tackle the persistence bit. So the way things are done now is the collectors, so whether you're going to get SNMP data, HTTP data, anything, end up gathering all these values and put that into a collection set. So that collection set was then sent to the thresholder, so thresd to manage all of your thresholds, send events, alarms, etc., and to RRD, right, for persistence. So what we did was create a layer of abstraction there called the persister, and what happens is based on your configuration, it'll go to either one or the other, right? So with the current, the way it's structured in 17 right now, you can persist to either Newts or RRD, not both, right? And again, in the case of Newts, we'll go out to Cassandra data store. RRD, we'll just write to the files on disk. Cool. So in the case of the Newts persister, what we're going to do is we're going to convert that collection set to a series of samples. So that's the structure that we showed earlier, and that's what's used within a Newts API. So then those samples are going to be pushed to a ring buffer. So this ring buffer is of a fixed size, lives in memory, and that's sort of used as a temporary queue, right? Then we're going to pop off those samples in smaller chunks, right? So the way, if you remember the second slide, the Cassandra nodes, there was that coordinator there that sort of acted to go and put or get the data in the appropriate boxes, right? So based on where these samples live, if you got a large chunk of samples and those live on all these different nodes, that coordinator is going to be doing a lot of work to put all these in the right spots. So what you want to do in most cases here is actually keep that chunk size small. So we'll just pop a few samples off the ring, and then we're going to put them in the samples table, that first table that we saw, and then put them in the terms table as well with the indexing so we can find them later, right? one of the things is that the terms, the indexes, don't change that much. Once they're indexed, we don't need to write those out again, unlike the values. So there's an intermediate cache there that kind of keeps track of what's already in the database and what's not to prevent us from doing those additional writes. So that cache can either live in memory or in an external process. And so typically it's fine in memory unless the cardinality, so the number of different samples you have is very, very large that can't fit, in memory on a particular system. But for most use cases, that should be fine. Another issue there to keep track of is whenever you restart OpenNMS, so on a cold start, is that cache will typically be empty. So there'll be these additional writes during the period where it collects all these samples for the first time as the cache is primed. All right. So that's the Newts persister. So we're going to look at the current resource model, so the way that we access and index resources in the RRD world. So the term resource is kind of confusing because we use resource IDs in OpenNMS to mean something and resource IDs in Newts to mean something different. So it's kind of tricky. One kind of maps to the other, though. So in the RRD world, we have files on disk, which are placed in a certain hierarchy based on the resource type, right? So if we're collecting node-specific data, we'll put that in the top-level folder here. Well, SNMP1, which is the node ID, and we'll put that all in an RRD there. If we're collecting interface-specific data, we'll have a subfolder here for the interface and put the data there. And if we're collecting data for something like a disk, then that folder is going to be, that data is going to be 2 folders down, right? So that's the actual files on disk, and those are the resource IDs that we use to refer to those, right? So textual representation, so the users don't have to know the explicit path on disk. So with Newts, everything was based, so with OpenNMS, everything was based on these resource IDs. So we kind of wanted to bridge that concept over instead of having to rewrite all that. So the way that we would approach that was as follows. So the resource ID in Newts is equivalent to the path on disk of the RRD files, right? So those were unique, right? Because every RRD file would have its own path on the file system. So what we did was just bring that over here. But then, in order to be able to find these things, it's very inefficient to do long queries like we had seen before, like the RC colon amount to doing the Cheerwine, because we have to pull that whole result set into memory and do that. So what we did was add these extra sort of synthetic attributes on the resource that allow us to index and find it quickly, right? So what it stores is basically that path there. So SNMP2, ETH0, right? So it'll store the length, so the depth of that resource, and its various bits, right? So the first index will be just the first part, second one will be part 1, part 2, and it stores the length in that last bit. So these are the entries that are going to end up in that term table that we saw there before, right? So that allows us to look up the resource IDs with these simple queries. So this is all done behind the scenes, so you don't actually have to worry about this too much, but it's good to know how it works. So that helps us populate these sorts of tables here that you're probably used to seeing whenever you go to look at the performance graphs for a particular node. So now that we have the data and we're able to persist it, we're able to find it, what we need is a way to go and fetch it. So in 16, we added the measurements API, right? So that's sort of an abstraction over retrieving the data, kind of like the opposite of the persister, right? So the measurements API will provide a consistent interface to get data, whether it's stored in your RRD files or within Newts, right? So the request, we tell it which resources we want, what expressions we want to apply on that. One thing to note is for the expressions we use Jexel, which is a lot to be able to perform mathematical expressions, which is much easier to read than RPN notation if you've ever had to work with that in the RD tools. And something new in 17 is that we actually have a set of filters that can operate over the result set. So what those are is basically bits of code that operate over the result set before it's returned to the client. So you can go ahead and fetch all this data, right, and it'll return you a table and saying, here's all the values for these metrics at these various times, and then pass it over to these blocks of code. And they can do things like remove any leading or trailing nons, so let's sort of compress the data set. In some cases, you won't really care about those, right? It could do things like remove spikes. It can do things like interpolation. So let's say you have a few missing values within that data set. These filters can be used to fill those in or do anything really, just munge with that as much as you like. So a simple interface you can implement to mess with that data. We also have an interface to R. So that's for statistical numerical computation. So you can have actually code that executes in R that operates on that as well. So we use that for forecasting, so Holt-Winters-based forecasting. Instead of implementing those algorithms ourselves in Java, we just add an integration with R, which already supports all that, and did it there. So all that's available through the measurements API. And like I said, that works whether you're talking to whether your data is backed by RD or Newts. And in response to that, we'll get the data set that we want with all the filters and expressions applied. So that solves our problem of getting the data, right? And our abstraction there, whether it's RD or Newts. So then we'll look at graphing. So I think Tor showed this very image on his keynote yesterday morning. So Backshift is a JavaScript library that uses the measurement API to pull in the data and generate graphs that look like RD graphs. So the way it achieves this, it actually uses the existing RD graph definitions instead of you having to create new ones, because OpenNMS already ships with a wealth of these, so we wanted to leverage that as much as possible. So it'll actually go get the RD graph definition, parse that, figure out what it needs to get. It'll generate that request to the measurement API and fetch the data and present it in a similar fashion. So a couple of things to note. The graphs are now, they're interactive, so you can scroll, you can zoom. That little button on the top right, you can use that to copy the raw data to your clipboard in CSV format. So looking at that, you can click that, Control-C, and then paste the results into an Excel spreadsheet, right, and look at it that way. So some pretty cool stuff that we could do now with those. Now these graphs are actually, by default, they're only enabled whenever you use Newts, but it's technically, you can set a flag to use these instead of the RD graphs, even when you're using our RD tool. So that's an option there as well if you want to try those out. So we can read the data, we can graph it, but now we introduced these Cassandra nodes into our OpenNMS setup, right? So how do we monitor those now? So OpenNMS already shipped with the JMX collector, so we leverage that, and the JMX poller. So we leverage that to monitor the Cassandra nodes. So we have configurations for polling to make sure that the Cassandra nodes are up and operational, and we have a series of profiles for data collection as well that'll collect things like read and write latency from the Cassandra nodes themselves. So that's all available, and that could be used as well, even if you're not using Newts per se, and just have a Cassandra cluster in-house that you need to monitor. You can leverage those definitions and graphs there to gather all that data. We do also have some Newts-specific metrics that we poll for about the Newts key space and the tables that we use in that case. But those can be also used as a good reference if you have other key spaces or databases that you want to monitor in Cassandra. So where do we go from here? So all this is new and shiny for all of us. In OpenNMS 17, there's been a lot of refactoring done to try to get this all to work. But again, it's still fairly new, right? So at this point in time, what we're looking for is the community to start trying it out and give us feedback into how we can improve things and go from here. There will be some things to change, of course, right? But we're looking at you to kind of help us get that going. So in its current state, it works. I mean, we have graphing in that whole stack. Everything I showed you there today isn't functional. Is functional. The documentation is in our official docs repo. Installation guide on how to get set up and going. And of course, if you have any issues with that, you could just shoot out to us on IRC or the mailing list, and we'll help you get going. There's a couple things that are still in the works, though. Like one thing is a tool to be able to export or import your RRD metrics into Newts, so that way you can sort of pick up and keep your historical data wherever you're at now. And I think other than that, all the major function points within OpenNMS are working. The only one that's remaining is statsd. If any of you guys use that daemon currently, that does not support Newts, but before OpenNMS 17 is shipped, we'll make sure to get that going there as well. And that's it. That's Newts. So there's contact information, link to the setup guide, and to the Newts homepage there as well if you want some more information. So I'm guessing there's a lot of questions at this point, so I'll open up the floor. I think Craig has one. No?
Actually, well, Matt, I do have a question. So, how does it handle timestamps? How do you know that you aren't getting remote devices with different timestamps sending data into Newts?
Remote. So right now, Newts is the same approach that we use to collect data today, in that we go and fetch the data, we timestamp it, and then we push it out to Newts. So at this current point, there's no sort of availability to push data into it, right? It's strictly on a polling basis. But after these last few days, talking with people and things like the Internet of Things use case, we're just trying to think that that's something that we'll have to add there shortly. Does that answer your question?
Are each of the samples individually timestamped?
Yeah. So if I go back.
And is the timestamp in numeric?
Timestamp is numeric, milliseconds. Yeah. Everything in Newts is in milliseconds. Yeah. Allow that finer grained precision, and because in RD it's all seconds, so you can have that little. On the OpenNMS server, make sure that its clock is properly synchronized. Yeah, it wouldn't hurt. Just for like RRD as well. I think we got a question over there. I'll come back to you, Listen.
Yeah, sorry, just if you wanted to knock together this with version 17 for yourself,
Yeah.
What resources will it need? Will it all fit in just one VM? Just throw them all together, or does Cassandra need a couple of nodes?
So it depends on the amount of data that you're storing within Cassandra, right?
Small to begin with.
Yeah, so that's fine. Then you can just put it all in a single VM and play around with it. So Cassandra itself is meant to utilize the resources of the system as much as possible. So it'll take advantage of memory, it'll take advantage of the CPU, and it'll take advantage of the disk I/O. So it kind of has a hog all of those. So, so just keep that in mind if you're deploying that into production. You probably want to put your Cassandras onto a separate machine than the OpenNMS instance, so you don't have any contention there. But I mean, I fit that the whole stack, OpenNMS and Cassandra within a 2 gig VM, just for testing purposes. So it is possible. Dustin, you got a question?
There is a single node installation guide available which reduces the memory footprint and all that stuff on the Cassandra's page. Looking at this, the sample, what about things like strings, and what do you do with type? So is this information also stored in Newts, or is it still OpenNMS specific?
So no, that information is actually stored within Newts. So the type and the actual value are encoded in the value blob here. So the first, so value blob, 9 bytes, first byte used to store the type, remaining 8's the actual value itself. All right.
And what about string
So-
values from SMP or something like that?
So the string values are stored within the resource attributes here.
Nice.
So that's actually, I didn't denote that table here, not to make things even more confusing, but a table similar to this, that all the resource attributes and key value pairs are stored, right? So that brings up a good point, though. There's two different things. There's resource level attributes, so key value pairs stored on your resource, and there's also key value pairs that can be stored on your sample. So if you want to tag samples with specific data as well, that is possible. Marcus?
Do we have a REST API so that I'm able to create my own feeder to push data to OpenNMS and to store it in SQL Server?
So Newts can be used as a standalone project as well, just with its own REST API, and so anyone can use it as a generic time series storage engine. But if you want it to be within OpenNMS itself, though, there's no way to currently push data in and have that associated with a node. So that data currently has to be collected from OpenNMS using one of the existing collectors.
You could write a new collector that eats from an MQ.
Or something of that nature. But yeah, there is I mean, we've been talking about that just at lunch here, that, you know, that'd be interesting to sort of add that. So what's your use case there?
You have this use case when you don't use any SNMP agent or you don't pull any data from an agent, or you have your own agents and you want to send performance data to Newts and to graph them in OpenNMS.
Yeah. So yeah, that's something we'll look at adding there very seriously.
Common use case.
Yeah, no, yeah. Just OpenNMS was like traditionally a pull or collect, whereas I think now a lot of the new solutions are doing push instead. So I think we need to support that there as well. The only challenge is being able to associate those metrics that come in with the OpenNMS model, right? So there'll have to be some data there that's tagged and say, hey, this is associated with this node, this is this resource, etc.
Yeah.
So provided that that's tagged, then that should be straightforward.
Also stuff like thresholding and all that, mechanisms around the data collection will become more complex if you can't assume a regular interval. So you have to rethink some of the models to make it possible.
Yeah.
But just storing the data, you can, as he said, you can use Newts on your own to just push the data in there.
Yeah, that's right. When you think it the old way, but when you think about a new concept where you have these thresholds, or when it's a separate or a microservice. Sorry for that. when this would be a microservice, then you can separate this functionality, and you would be able to reuse it or to push your data there. And maybe to write your own collector.
Yeah.
So
It's very valid. Yeah. The only challenge is the association and, you know, reworking our existing components to support that. But yes, yeah, I think it'll be a thing that's worthwhile to do.
What support is there for reporting based on the data?
So reporting, there's the existing facilities, right? So there's the graphs, the KSC reports. And there is also Jasper reports as well that were used to pull in RRD graphs and time series metrics there. So we've kind of reworked the Jasper engine to go and use the same services that the measurements API and the REST offers, so that it's kind of agnostic to the actual persistence. So the reports that are shipped with OpenNMS, or the ones you create on your own, will work with either RRD or Newts backed data sources.
Is it fair to say that it should be much easier now to develop Jasper report templates
So,
versus the old RRD regime?
right, so we actually reworked that whole ecosystem around building these reports and how to reference and pull that data in. So yes, it will be much easier.
The binary RRD tool driver and the fields provider and all of that other stuff.
No, so from the Jasper Report Studio perspective, if any one of you have worked with that before, you're able to just pull in our library, and then talk to OpenNMS via the REST API into the database. You no longer have to have access from that machine to those IRD files, right, as you did beforehand. So it makes it easier to develop these reports now.
You could have a Jasper server running your reports.
Yeah.
I mean, run inside OpenNMS.
Yeah, exactly.
Are there any mechanisms for exporting data into other tools like MATLAB or the like?
So the ways to get the data out, there's the measurements API, which you can write, your queries for and pull that in. We can provide some example scripts on how to get that into wherever people need it. And there's also the graphs. So that little box at the top right. So if you're looking at something interesting, you want to analyze it in Excel or in MATLAB, you could just go ahead, copy that to your clipboard and paste in the CSV format. So those are the existing facilities that are there. Oh, anything else?
Can you say any more about the R stuff you've done?
Let's see the R stuff. Not really. So the R integration, the way that works, it'll just, it's a simple interface between OpenNMS and R. What it does is it passes the R scripts a table and expects a table back in return. All right, so your R scripts can then perform any calculations you like. There's a wealth of libraries that are available for R for doing Bayesian analysis, all these different things that you can do on that, and then get the data back in. One of the limitations of the current structure, though, is that we actually do like an exec to R and pass the input via standard input, standard out through the R process, right? So I think some improvements there would be to actually, I believe there's R engines that are available in Java, so to be able to use one of those would probably be a lot more performant as well.
When you're working with filters, whether they're in R or in Java, I guess.
The same.
How granular is the set of data that's passed into the filter, and is that adjustable? Like, can you say, give the whole collection set to this filter, or is it just like?
So let's assume there were no filters,
Okay.
right? Whatever your query is, whatever granularity in the data that you get in your query,
Oh, right, because this is when we're fetching, not when we're
that
storing.
is passed to the filter
So
level.
however much we ask for when we scope our query is how much we get, and we can do it any monkey.
And then your filters can be chained, or your filters are chained if you have multiple, so you can have various levels of processing.
Okay.
So, for example, if you want to perform forecasting, there are several things you need to do, but you can't just forecast. You got to sort of clean the data before, right? So one thing you'll do is remove the non-values, right? So anything that comes before or after the data set, chop those off. And then you're going to have your data set, but that might not be, there may be missing values in there as well, right? And most forecasting algorithms don't like that. So what you'll do is interpolate. So you'll have one filter to truncate, another one to interpolate, but then, oh hey, you may have spikes and counter wraps and things like that, they're in there as well. So then you add another filter to remove these outliers from the data set, and then your final phase will be to perform your forecast. Right? So you can do whatever logic you want over top of that.
We should be able, as long as we make a query that's sufficiently broad, we should be able to do things like look at different instances of the same resource type, or even resources of disparate types, compare them somehow to each other. Like, as an example I always give is like the 5-minute load average as it relates to the currently logged in number of users.
Yeah, you can do that. Yeah.
Stuff, scalars versus multi-instance thingies.
Yeah, so you can do all that logic within those filters. If you can't do it within a simple expression, yeah. So if you want to do something like that, yeah.
Nice.
Anything else, Marcus?
Am I able to use it with the last version of OpenNMS, or is it the 16 version?
So 16 supports everything up to here.
Yeah.
So it just doesn't support the filter bits, but the measurement API is present. So 17 adds the ability to add filters over the data set.
Do expressions also extend to the full data set?
Yep. So expressions work that same way, but they're not as flexible.
Does
So-
Jexel have the richness to express the motion of traversing across resource boundaries?
No, not really. You'd have to do some weird conditionals, and you could probably do it in a Jexel expression, but it wouldn't be maintainable. Yep. Cool. I think it's a good point to stop. If you have any questions, come see me. Still here for the next little bit. And there's my contact information. Thanks, everybody.